All right, how's it going, everybody? We are here on Thursday, March 4th. We're going to be talking about section 8.1 today. We're talking a little bit of arc length. I do want to point out before we even get started right here, you should see that our two sections here to start chapter 8 are arc length and surface area. So now that we're back into chapter 8, we're back into looking at some more applications of integration. And so just like we saw in chapter 6, a bunch of these applications are geometry based, right? So this is going to be really nice. I really like this 8.1 and 8.2. This makes me feel like I actually understand how integration works when I cover these two sections right here. This is like this just if you were to say, "Hey Tony, what does your calculus intuition tell us we should do in this case?" It's exactly what we're going to end up doing. It like really matches up perfectly with like again, not like my academic training, but with my like very generic intuition about what does an integral do. I feel like this nails it here today. So I hope that you find this formula as satisfying as I do as we derive this thing here today. And so I'm going to kind of explain that right here. Before we learned calculus, what were we capable of doing? We could find the slope of only straight lines. We could find the area of only special geometric shapes, basically squares, triangles, rectangles, circles. Anything other than that, it's either extremely difficult or impossible to geometrically find an area. We could find the length of only curves that are straight, with the exception again of something like a circle, where somebody gave you a formula where you didn't know where that came from for circumference of a circle, right? Now that we have calculus, what we know is that we can use the derivative to find the slope of any curve, not just straight lines, right? And we do that by thinking of 2 points being infinitely close together and computing a slope between the two of them. Now that we have calculus, we can find or at least estimate the area underneath, and I'm going to say any curve here. Integration, as we know, is much more fickle than a derivative, but uh, any algebraically defined explicit curve in 2D space, we can find the area underneath by taking an infinite number of infinitely narrow rectangles and adding them up underneath the curve, right? That's all an integral is. We're adding up an infinite number of infinitely thin rectangles. The third bullet point is our one for today right now, which is that I think that you should think of length as being something sort of like slope and area, where it's something that we could only do in a special case before. We're now going to make it something that we can handle in a generic case because we know calculus. So how are we going to find the length of any curve? Well, let's think about how all these things were related up here. Before, we could find the slope of a straight line. Then to find the slope of a curve, all we really did is we still thought about slope in our linear sense. We just made our delta x infinitely small. When we could find the area underneath only special geometric curves, things like rectangles or things like triangles, what we then did is we said, well, listen, let's still just think in terms of that most basic object, just a rectangle still. Or I guess we saw in chapter 7, we could think trapezoids, we could even think parabolas with Simpson's rule, but still, a Riemann sum with rectangles, as long as you take a limit as the width of the rectangle goes to 0, gets infinitely small, then we get the exact area right there. So again, we are estimating, or sorry, we are setting up our calculus statements based on our simple statements, right? We still defined a derivative, we still defined an integral based on straight line thoughts and on rectangle thoughts, even though they got us all of our curves information, right? So same thing here. When I'm thinking about arc length of a curve, I still want to think about all of my straight line thoughts out here, the length of a straight line. And so just as with derivatives and integrals in general being based on linear type computations, so too will this be based on a piece of line information right here. So what I'm thinking to myself is if I want to find the length of a curve, I can just think of that curve as being a whole bunch of infinitely short pieces of straight line, find all those lengths, add them all up. All right, that exactly follows my intuition. So I want to be just real clear here. You should definitely be saying to yourself, yeah, that sounds totally reasonable right now because you've done enough integration that you've seen like 20 different things that we do with integrals and they all follow this theme. Come up with a generic object that's representative of all of the infinite number of objects, add up all of those objects of interest. That's exactly what we're going to do right here. So I'm going to just say it again right here. I think this is a super natural calculus idea that exactly agrees with every bit of intuition we've developed about what happens in calculus here. All right, so here's our idea. Our Riemann idea in our setting right here is to estimate the arc length of a curve or I guess not to estimate, to calculate. Okay, no, this is our estimate right here. To estimate the arc length of a curve, we would take a sample of n points on the curve. This should be looking to you a whole lot like a Riemann diagram right now, and just find the straight line length between each pair of adjacent points, and then add up all those lengths, right? So in this case right here, and I've got my pre-selected colors because this is just an image I found on Google right here, but it's exactly the one that I want. I've got a red curve here, but what we can see is that we've chosen 1, 2, 3, 4, 5, 6 points on the curve, computed a straight line distance from point to point. And if we just added up all those blue line lengths, which you learned how to do in like eighth grade or something like that, I don't know, whenever you learn the distance formula, that's all we're going to do today is basically just the distance formula. Um, we add those up, we're going to get a pretty good approximation. Honestly, I think these blue straight lines are going to give us a pretty decent approximation right here. Certainly going to be an underestimate because the shortest distance between any 2 points is going to be a straight line right here. So this blue estimate, certainly going to be an underestimate for the actual arc length right there. But that's not even bad with even 6 subdivisions right there. I think that's not too crazy, or 6 sample points right there. So I hope that I hope that you feel comfortable with me saying my next word right here. So obviously, what we're going to do is we're just going to use more points. And I always am nervous to say obvious because I don't want to insult anybody to whom something's not obvious. Lots of things in math are not obvious till you're very comfortable with them. I hope that this feels to you exactly like everything you've been doing for 2 semesters at this point right here. We form an estimate, and then we make the estimate better by increasing the number of subdivisions or decreasing the width between subdivisions, however we want to think about it here. So here's our limiting idea. To improve our estimate, we take smaller subdivisions of the line. We let our delta x term, our measurable finite amount right here, become dx, our infinitesimally short length right there. And we add up all those lengths. Well, literally the integral symbol is an S to stand for sum because we're going to sum all those up. Microsoft Word, I hate it when you just red squiggle under 2 letters of a correctly spelled word. Get out of here. So what we should be thinking about here is putting down an infinite number of little slope triangles on our curve here. But now instead of using those, what I've referred to when I teach algebra as slope triangles on a curve here, we're not using those to measure rate of change so much anymore, which you can see. Here's our dy dx. This is exactly like our derivative diagram right here. But in our case now, we're not interested in getting this measurement of dy over dx. We're actually interested in getting this measurement of the length of the hypotenuse. This is going to be one infinitesimally small piece of the infinite number of small pieces of arc length that we're trying to add up, is this length right here. So what you should see is that this is literally the formula that we're interested in right here. If this is an infinitely short segment of the curve, dy dx, then the length of this hypotenuse, we're going to want to add up an infinite number of hypotenuses here basically, is going to be the square root of dx squared plus dy squared, where dx and dy are the infinitely short change in x and change in y for any one of our subintervals right here. So like, I kind of hope that like you already like are down with what's going to happen right here. The formula is basically just going to have this in it. We just need to lightly rearrange it. I think that this is a very, again, very natural usage of an integral right here. I don't think this should feel like everything you've ever done with integration right here in a very sensible idea right here. So let's go ahead and derive this formula for this thing. And along the way, I want to give you a light math. I'm not even going to do a good job of defining it right here, but there's a word that we should throw out here. What's the requirement for being able to perform this arc length computation? We want to find the arc length of a smooth function y equals f of x over the interval x from a to b. Nothing too weird right there, except that the word smooth very much seems like it could be a generic word, but it is in fact a technical math definition. Smooth to me means not just continuous, because I'm thinking absolute value is continuous, but it's not very smooth. It gets to a point down there. When I think smooth, my intuition tells me that that should be the same thing as differentiable. But smooth is actually stronger than just differentiable, because differentiable means you can take the derivative of it. Smooth implies that all of the derivatives are possible to be taken and are all going to be continuous. And by the way, smooth is actually used. I think that generically, when people use smooth, they mean that you can take an unlimited number of derivatives, but there are several, and then we're getting into like a bunch of technicalities about a bunch of things that you guys aren't going to look into until you go to grad school, because you're all going to go to grad school. But sometimes some things only require that we know that like the first 4 derivatives are going to be continuous or something like that. And so there are sort of ways to specify your sort of degree of smoothness. How many derivatives can you take that you're guaranteed to still have a continuous derivative down there? In any event, the whole point here is that we're saying that's sort of the one type of thing that we want to watch out for here is that our sort of restriction on this is not just a continuous function or a differentiable function, but technically this should be something that works for smooth functions, functions that have any number of continuous derivatives out there. So let's go ahead and see what our formula is going to look like right here. So as we saw from our diagram one moment ago, if we're thinking of like a curve out here in space, we want to find the arc length perhaps from A to B. And so what we're going to want to do is we're going to want to look at one generic subdivision right here. That's going to be delta x wide. All right, so we could look at one subinterval where this width right here is delta x wide. And from this point to this point, we should be able to, okay, I was hoping to get a triangle in right there. Maybe I think I know what I need to do right here is I need to make a curve that's actually got a little bit of shape to it here. There we go. So there's my A point, there's my B point. Now when I look at this guy right here and I look at the ends of this delta x region, there should be a tiny little triangle right there that we can mark off right here. So what I'm going to do is I'm going to grab, that representative triangle right here. And I'm going to say, let's grab this guy right here and go take a look at him over here. What we want to kind of estimate right here is saying to ourselves, this estimating triangle, once we've zoomed in far enough, it is that's like literally the definition of being differentiable is that you can zoom in far enough and your curve just starts to look like a straight line piece here, right? So this is going to be our dx, that's our infinitely small piece of x change. This is going to be dy, our infinitely small piece of y change. And this is going to be the length of that one Riemann object, the length of a single approximating hypotenuse. And if I continue with my Tony trend that nobody else really says these things, but I like to kind of say all these kinds of words to help me keep track of it in my brain, I might go so far as to call this a Riemann hypotenuse right there. I don't think any mathematician's ever said that before. Kind of a ridiculous thing to say. But the point is, anytime I use Riemann as an adjective, I mean it is a representative of an infinite number of things that I'm going to add up. That's what I mean when it's a Riemann something, right? We've been talking Riemann objects. This is a Riemann hypotenuse here. And we easily know how to compute this, right? Dx squared plus dy squared equals L squared. And therefore L is going to be the square root of dx squared plus dy squared. So on the one hand, that was really easy to come up with our general object that we want to add up a bunch of. On the other hand, what the heck does it mean to have that dx and that dy in there, kind of like a solo thing right there? Well, let's go ahead and see that we can just do a light bit of algebra to make this look exactly like something that we can handle right here. So total arc length should be the integral then from x equals a to x equals b of L. But what does that mean, right? We're adding up a bunch of arc lengths right there. The thing that I hope that you're saying to yourself that's obviously missing right now is like, what are we doing here? Is this like a time? Is this times dx or something? And the answer is no. If we were to stick a dx onto this right now, then you'd be doing length, which is we can think of that as like meters, times dx. That would be giving us meters squared. That would be like area. We're trying to get length. So notice here, there is not a dx that's stuck onto the end of this. The dx is contained on the inside. Our issue right now, though, is we don't know what it means to just have a singular dx, a singular dy. So what we want to do is we want to break this down, do a little bit of algebra on the inside. That'll be pretty simple right here, and we'll be in a usable format right there. So the dx is there, but notice like so is the dy, which is a little bit weird right here. And so all I'm going to do though is I'm just going to factor out a dx squared. And by the way, we're going to write this formula two different ways right here. So I'm going to kind of branch this off into two different branches right here. X equals b. And what I'm going to do here is I'm going to factor out a dx squared. And notice that if I factor out a dx squared from this guy, what I'm left with is a quantity on the inside that does make sense to me. dy dx is something I can do because I've been given a y equals function. Dx squared as a factor underneath the square root is just going to pop out to be our dx on the outside. So it looks like our arc length formula is the square root of 1 plus dy dx squared dx. Alternatively, what we could have done right here is we could flip this around a little bit right here and say from x equals a to x equals b. But instead, maybe I want to factor out the dy squared. Oops. We could certainly just use this formula with x and y's roles being swapped. So if you were given an x equals equation, then you could just use this setup right here. Notice my bounds of integration are currently in terms of x, so it looks like I'm going to want to get them in terms of y right there. So I might go ahead and say that this would be like f of a, and I guess I'll go ahead and be actually responsible here and literally say y equals f of a. So y equals f of b. And this should be the integral from 1, or of 1 plus, oops, I dropped my square right there, that matters, 1 plus dx dy squared dy. So this, I think, is our more typical formulation of this guy right here. But again, if you were given an x equals equation, it should be no issue whatsoever for you to come up with the, to use this formula here as well. We're just swapping some variables here, so. Right, so it just depends. Do you have a y equals equation? Do you have an x equals equation? Pretty nice and easy right there. I think the derivation of this formula is a piece of cake. We literally didn't even do anything. We literally just threw the distance formula into an integral and called it good. Did a very light algebraic rearrangement, one that you're already comfortable with because this factoring out squares underneath the square root should feel a whole heck of a lot like all of our trig integration that I feel like, man, we covered trig integrals in like 7.2 and they have not left us alone for weeks at this point. And you should notice that we're now going to be getting the square root of 1 plus squared terms here. Yeah, it looks like you should be expecting more trig integrals right here. So the reason why this waits until chapter 8 is because it's just very, very common for trig substitution type of integration being required to handle these integrals right here. So the setup for these, pretty easy. It looks like you're going to take a derivative, square the derivative, add 1 to it, take a square root, then go ahead and try and evaluate the integral here. So there is actually a derivative contained within the integral here, which is a little bit interesting. So I hope you remember some derivatives here. That's usually not too big of an issue right there. So let's go ahead and do the thing here. So as it always goes, anytime that you're in math and you're learning something that's new and you see a formula that doesn't look like something that you're 100% confident in, then what you should always do is verify this against something that you already know the correct answer to. That helps us get more comfortable with these formulas. It helps us feel good that we're doing the right thing. Because as I'm positive that all of you guys have felt that you've been doing some math in the last few weeks where you're like, I don't know if this is right. We should verify that things are going the way that we expect them to go. So verifying formulas, I think, is this is always the stuff that like made me feel good about the math that I'm doing here, which is why I always try to force this in these lectures here with you guys. So let's just find the circumference of a circle. Basically, that's an arc length, right? And I should say to you guys again, how do you know what the circumference, like how do you trust the formula for the circumference of a circle? I honestly don't think that you should. I think that the reason that you trust it is because your sixth grade teacher told you that that's what it was and you just blindly believed back when you were 11. It's not like your sixth grade teacher was wrong, but like you're an adult mathematician now. You don't just believe things because people tell them to you. You verify doing the math. And so we're going to do that right here. So let's find the circumference of a circle with area 3. Let's just write down what answer we know to be correct right away because we just straight up know this right here. And I'm thinking to myself, circumference equals 2 pi r, which in our case is 2 times pi times 3. And so it looks like 6 pi is the correct answer to this problem. That's what we're hoping to arrive at, but I'm hoping to get there by obviously using our arc length stuff right here. So the thing I'm thinking to myself is one of the many things that we like about circles is that they have an infinite number of lines of symmetry right here. So this is my circle that I'm interested in, but what I really think I'm going to do, since I'm not very smart, but I'm smart enough to know that I can be lazy, right? I want to reduce the work that I'm doing right here. So what I think I'm going to do is find just this arc length and multiply it by 4 here, right? So what are we doing right here? Well, it seems to me like if I'm going to set up an arc length statement right here, what I'm going to need to do is come up with the equation of this circle right here, right? So it seems to me like we're going to be getting our circumference is equal to 4 times the integral. It looks like x is going to go from 0 to 3 of the square root of 1 plus dy dx squared dx, right? So it looks like what we need is a dy dx, and if I need dy dx, that means that I need y, right? And so our circle equation is x squared plus y squared equals 3 squared. So it looks like I can solve this guy for y. Y squared is 9 minus x squared, and y equals, technically there should be a plus or minus on the square root, but I'm only considering the top part of the circle, so I'm cool with just keeping the positive part. And it looks like what we now need is we now need dy dx to go ahead and throw this into our integral here, right? So let's now go ahead and find dy dx with this guy. Maybe come over here. Dy dx. Well, the integral, the outside function is the square root. That's a power of 1/2, right? So maybe I want to think of this as 9 minus x squared to the 1/2 is a little more helpful. I'm going to see 1/2 times 9 minus x squared. I subtracted 1 from the power, so it's now a negative 1/2. And I need to multiply by the derivative of the inside function. That's a negative 2x right there, right? So it looks like a little bit more simplified version of this guy is dy dx. Feel like I did a bad job starting in the middle of the page, and now I'm going to do a little on the left and a little on the right here. That's okay. Dy dx equals, it looks like my 1/2 and my 2 cancel. The negative is going to survive. It looks like this is a negative 1/2 power, so that's really 1 over a square root. And it looks like this x is just as a regular multiplier, so it'll be up in the numerator. So I think I'm going to get x over the square root of 9 minus x squared. All right, just a little bit of algebraic rearrangement of my chain rule stuff right there. So we've got a dy dx right now. So now I think we're good to go. I'm being very irresponsible here, but at least I'm drawing some arrows, so helping guide us along to where we're going here. So now I got my dy dx equation. Now I can go ahead and throw this into the integral of interest right here. So 4 is the integral from 0 to 3 of the square root of 1 plus negative x over square root of 9 minus x squared, that's all being squared, dx. Right? Now, this is kind of a bummer that we have a square root and a square root, but this square root's getting squared right here, so that's going to be slightly less of an issue for us right there. So what are we getting underneath this the square root right here? Well, I've got a 1 plus. Now this is a plus, so negative got squared, it's positive. X gets squared, it's x squared. Square root gets squared, it's just gone. All right, so this is shaping up. So it looks like I've got a sum underneath the square root right here. So I'm thinking I want to write this 1. I want to get a common denominator. So I'm going to write 1 as 9 minus x squared over 9 minus x squared so I can get a common denominator. It looks like negative x is going to cancel with positive, or sorry, negative x squared cancels with positive x squared. And what I'm seeing here is it looks like 4 integral from 0 to 3 of What do we got right here? All that's left is just a 9 on top. I can take the square root of 9. It's going to be 3. 3 times the 4 on the outside is going to be 12. Oh, and actually, I can now do one better because I've now evaluated the square root for the entirety of the numerator. So now this is just 1 over square root of 9 minus x squared dx. And now you should say, nice. That's what I'm hoping that you're saying right now, because this is now in a format that you recognize from our section in trig subs, right? So our setup here is pretty easy. Equation of a circle, pretty dang easy. Taking the derivative, not bad at all. Chain rule was involved. I threw that dy dx in here. I had to square it. That was actually helpful. It just got rid of a square root for me. Gosh, this would have been harder if we didn't square this thing in here, right? Getting a common denominator was pretty easy. This guy did reduce down to something nice. Notice even if that was like an 8 right there, I'd still probably write this as like 4 times the square root of 8 on the outside to evaluate that square root in the numerator, because I really had that desire to get, like, I don't know. I'm hoping that you guys, like me, as soon as you saw that like this 9 minus x squared was in here, I mean, even at like this line right here, I was thinking to myself like, oh, this is either going to work out so nice that the entire square root's going to get eliminated, or we're doing trig sub. That's kind of where I was at when I was writing this line right here. It doesn't seem like we were able to take the square root of quite every single term right here, but that's fine. We still got ourselves down into an obvious trig sub situation right here. So it looks like our substitution that we want to do right here, based on what we've learned from our all the trig subs that have ended up cropping up in the last couple weeks right here, is it looks like I can do 9 minus 9 sine squared, 1 minus sine squared will be cosine squared. So that's going to kind of be my goal swap here. 3 cosine theta d theta. And I'm going to use this substitution in here now for a 12 integral from 0 to 3, 1 over the square root of 9 minus 9 sine squared theta. Dx is 3 cos theta d theta. Get a little closer to this edge. Is that going to end right there? Here we go. So what do we got? It looks like here, I'm noticing that these 9s are going to pop out as a 3 outside of the square root, but that's in the denominator. There's a 3 that's in the numerator. So it seems to me like I could do some canceling. 9, 9, and 3 are all going to cancel right there. I'm left with a 1 minus sine squared, 1 minus sine squared underneath the square root. Well, 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. That's a 1 over cosine times cosine. Holy cow, can this get any nicer? The whole thing is gone. We literally did a sub and this reduced this down to literally the integral of 1 d theta. So I'm pretty sure I can handle wrapping this guy up right now. It looks like our answer is going to just be 12 theta evaluated from x equals 3 x equals 0 to x equals 3. And notice, by the way, I did do my irresponsible bounds of integration on this guy right here, in that I left my bounds in terms of x when in fact we had swapped over to theta, but I was being very careful with myself here. And so it does look like now we can either choose to swap out theta back in terms of x, or we could solve our x bounds for theta. Either way is fine. I think that I'm going to go ahead and say here that, let me get this back over here now. It looks like I could say something like x over 3 is sine theta. I just want what theta is. So it looks like theta is going to be sine inverse of x over 3. So it looks like I'm going to be getting here 12 times sine inverse of x over 3 evaluated from x equals 0 to x equals 3. Cool. We just got to evaluate 2 inverse sines and we're done here. Sine inverse of 3 over 3 minus sine inverse of 0 over 3. That's just sine inverse of 1 minus sine inverse of 0. What angle are we located at if the value of sine was 1? Sine is measuring height, so that's when we're at pi halves is when we get a sine of 1. So that's what sine inverse is going to be. Sine of 0, when do we get a sine of 0? When we're at 0 radians. No rotation gives us no height on the unit circle right here. Boom. Just like we were expecting right there, 6 pi. Very nice. So this, again, these sorts of verifications, these are the things that make me feel like, okay, I am very confident that we derived the correct formula, and I'm confident that I'm using the formula correctly because I know for a fact that that answer was supposed to be 6 pi, and I was able to follow my steps and get to 6 pi. I hope that this problem for you is a good justification as to why this is located in the book where it's located, because of the fact that there is inherently a square root that you are integrating when it comes to arc length formulas. It is often going to lend itself towards trig subs, just because that square root's in there, and we got to pop stuff out of square roots. That's by making things b squared when there's otherwise a sum of two terms, and the Pythagorean identity is what's always going to get us out of there. And I mean, hopefully that makes a ton of sense to you, because how do we get in the square root situation in the first place? The Pythagorean theorem, right? So like these are all like pretty closely related right here. Pythagorean identity, Pythagorean theorem. It's going to involve trig functions pretty typically when you're doing these arc length things right here, due to the 1 plus underneath, 1 plus a squared term underneath the square root. That's just screaming trig sub at us right here. So not too bad. It's certainly the case, by the way. I think I could have easily converted my bounds into theta right here by kind of just doing the same math up here. If I would have said x equals 3, then you would have said that theta was going to be pi halves, theta was going to be 0, and then you would have gotten pi halves and 0 for your two values of theta right there. Same thing. So I think that could have gone either way. So good first example. I feel good about what we're doing right here with this guy. So this is our, I'm only going to do one more example here because there's really just two things happening with the arc length formula, which I sort of think of as the forwards version and the backwards version here. In this situation right here, we were given a function, we were given bounds of integration, sort of naturally by just saying find the arc length of a circle. I sort of set those up for myself, but we had a function, we had bounds of integration, we wanted to know the arc length. In our next example, we're going to flip that around and we're going to say, I know what I want my arc length to be. I want to know what bounds of integration are going to get me there, right? So this is saying I do know the output. I want you to help me determine what inputs should be associated with that given output right here. So this is sort of inverting our process right here. Still going to involve our arc length formula, but again, in this case right here, what seems to be I do know where I'm starting. What I'm saying is I don't know where I'm ending. I don't know what my upper bound of integration is. I do know what I should be getting out from the arc length formula. The answer should be 10 out of that integral right there. Our job is going to be to identify what is the bound of integration that's going to get us there. If and again, we're picturing a fly traversing in space right here. And my question is, where will the fly be? If it starts right here and it's following some loopy curve out there, where will it be once it has traveled exactly 10 meters? That's the question that we're asking. So we know the arc length is 10 meters. We don't know what is the final location that's associated with that, given that this is the curve that's traveled along right here. So it's going to be kind of similar right here in that we're just using the arc length formula. But again, in this case, I don't know my upper bound of integration. I do know my desired output from the arc length integral here. So I'm a little smarter now based on the last problem. Not much smarter, but a little bit. And one of the things that I'm thinking to myself here is I know that one of the things I'm going to need right away is dy dx. I just know that that's one of the components right here. So I think my first move right here is just going to be to say, let's just get dy dx. It looks like that should be 2x minus 1/8. The derivative of natural log is 1 over x. And so I might write this as dy dx equals 2x minus, oops, that's an equal sign, minus 1 over 8x. All right. So it seems like what we're interested in doing here is we're interested in, I want to build my integral of interest here, right? So I'm thinking to myself that we should be integrating. I do know that my x location is starting at 1. So I'm going to say x equals 1 up to x equals, and the whole point is we don't know what's this x bound that's going to get us to an output of 10 meters. I'm going to call this unknown x value x star, all right? So x star is sort of what we're trying to solve for in this case right here. It seems like what we have for ourselves here is our arc length formula says 1 plus dy dx squared dx. So what I need to do is figure out some way to rewrite this. Now, here's the thing that I'm noticing immediately. This is not screaming trig sub at me as hard as the previous problem was right here. I'm not seeing like 1 plus a number squared quite pop out of this here. It's kind of unclear to me what I want to do with this stuff underneath the square root right here. So I think that I'm going to take a little walk over here algebraically to figure out what's going to go on with this square root term here. Um, so let's go ahead and see what kind of algebra we can do with this guy here. So I'm looking at uh, 1 plus 2x minus 1 over 8x. I'm trying to be a little bit more responsible with my page spacing. Oh, sorry. I want to go back real quick. I know, importantly, that this is equal to 10. I know that's a really important part of our integral setup right here. The only unknown is x star right there. And I would like to write my next line of the integral right here. And I'm going to be smart and do my little bit work of algebra over here, and then come back to the integral once I think I know what I'm doing. Because right now, I have no idea what I would do with this expression right here. Is kind of my issue, right? So since I don't know, I'm thinking to myself, I'm going to get out my algebra beaten stick, and I'm going to hit this thing until it looks like something that I can deal with here. So what's going to happen here? Well, I feel like I want this 1 somehow incorporated with this guy right here. So I feel like I want to multiply this guy out. So what am I going to get? 4x squared, 2 times this guy right here. If I multiply 2x times 1 over 8x, the x's cancel. 2 over 8 is 2 over negative 1/8 is negative 1/4 times 2 is negative 1/2. And then I square the term on the right, and that's going to give me a 1 over 64x squared. So the good news is 1 minus a half is just positive a half right here. So it looks like I'm getting 4x squared plus 1/2 plus 1 over 64x squared. Now I'm looking at this guy and I'm asking myself, do you know how to take the square root of this yet? And the answer is definitely not. I don't feel like I'm necessarily any closer to like being able to handle this integral yet. So I'm just piddling along right here. One of the things that I feel like I see here is this. One, I hate that 1 over 64x squared term. It's bothering me a lot. I don't like that fractional term associated with like quadratic terms right there. The other thing I'm seeing that's nice though is that both these numbers, 64 and x squared, are perfect squares. And in fact, so is 4x squared. So like I feel like it seems like I want to move towards like factoring some stuff out and getting it out of the square root, right? That I mean, the whole point of the square root's really jamming us up here as well. So what I'm thinking is the two things I hate the most about this problem as it stands is the whole thing's underneath the square root, which is an issue. I wish I could factor perfect squares out of it. The other thing I'm seeing here is I hate this 1 over 64x squared term. I feel like I want to factor out 1 over 64x squared. Both of those hates are converging on something very conveniently for me right here. So what I'm going to do is I'm going to factor out this 1 over 64x squared right here. And what happens when I do this? Remember that factoring is like a dividing process, but I'm dividing by a fraction. So it's really like I'm multiplying 4x squared by 64x squared right here. And what's that going to leave me with? Well, 4 times 64 is 256. X squared times x squared is x to the fourth. You should stop for a moment and convince yourself that if you multiply this back through right here, that we do in fact get 4x squared. My next term here is that 1/2 is getting effectively multiplied by 64x squared. So this seems like this should be plus 32x squared. And then this guy out here on the end, the whole point is I factored out the whole thing. So we're just getting a 1 right here. So now I'm looking at this and I'm saying to myself, you know what? This term right here, I'm basically good with this term because this is a perfect square. I can write that as 1 over 8x squared, and that can get pulled outside of the square root right here. So I have one term has escaped. I'm now wondering if the terms in the parentheses can also escape this square root, or if I'm going to have to deal with this fourth order polynomial underneath the square root. Here's the thing that I'm also seeing with this guy right here. What I'm seeing is if I think of, let me get a smidge of color right here. It looks to me like this looks like some, these are both perfect squares right there, right? This guy right here is 16x squared. If a is 16x squared, then you square that and you get 256x to the fourth. B is just 1. And notice 16x squared times 1 is 16x squared. And you double that and you get 32x squared. Oh my goodness, that just worked out real dang nice right here. So there's two algebraic moves I'm going to do going into the next line. 1 over 64x squared. I'm going to do myself a favor and write this as 1 over 8x squared. Because I want perfect squares so that they can come out of my square root up there in a second. The other thing that I'm seeing here is this looks to me to be like this is a perfect square binomial here, right? So it seems to me like this is going to be 16x squared plus 1 squared. Worked out pretty dang nice right there. So what I'm thinking to myself is that now I think that I can handle taking this integral because what I have done is I've done a bunch of algebra on the stuff that's on the inside. I've forced the entire inside to be written as the product of two perfect squares. I can just individually square root both of those things. We'll have canceled out both of those square terms. With the square root term in the integrand, I think I'm just doing direct integration at this point right here. I think I'm all good to go. So I'm going to go ahead and drag this guy back up to the top. We're done with our algebraic foray here. So let's go ahead and return to our integral here. So this is going to be from x equals 1 to x equals x star, the special x location of the square root of, and what do we just come up with down here? The square root of 1 over 8x squared, 16x squared plus 1 squared dx. Right? And again, there was no reason for me to do all this algebra within the integrand right there. This is a great time for you to say, oh, it's my side work here. Let's go ahead and algebraically manipulate the integrand. Once I get to something where I think I can handle it, we'll go back to the calculus component of this here. So I think we're there. And this is equal to 10. All right. So it looks like now we can go from 1 to x star. I don't need to keep writing x equals. Squares and square roots are gone. So this is a 1 over 8x times 16x squared plus 1 dx. We're just doing some regular old integration right now. I think I'm going to pop out that 1/8. And I've got 1 over x times 16x squared. So that's just going to be 16x. 1 over x times 1 is just 1 over x. I think I'm going to multiply both sides by 80, I guess, or by 8 to get 80 on the right over here. And then I'm integrating, right? I guess I don't even know why I'm writing this out as its own whole line right here. It looks like I'm going to be getting 8x squared plus the natural log of x. Oops, hold it. Evaluated from x equals 1 to x equals x star equals 80. All right, so let's go ahead and evaluate this guy. It looks like I'm getting 8x star squared plus the natural log of x star minus 8 times 1 squared plus the natural log of 1 equals 80. Over here, I see that I'm going to get 8 plus 0. This is just 8 plus 0 right there. So it looks like my total response here is, and I'm going to go ahead and just add this 8 over to the other side right away. It looks like I'm getting 8 x star squared plus natural log of x star equals 88. Now, you should notice that an important feature of this thing is that we don't have a way to solve this. Hang on, I got to scroll a little bit right here. Uh-oh, that's concerning. Okay. All right, so we can't algebraically solve this guy. All right, so again, I'm just going to go to Desmos and throw in this equation right here, or throw in rather the left side and the right side separately, and let's go ahead and find their intersections here. Um, let's go ahead and do that. So let's pop over to Desmos here. Over in Desmos, the two things I want to be checking out are I've got 8x squared plus the natural log of x, and I want to see when is that equal to 88. I know I'm looking at y equals 88, so I better get scrolling up right here. Okay, sorry, Desmos. Y equals 88. There we go. And it looks like this point of intersection should be exactly what we're looking at right here. So it looks like 3.294 is the x star value of interest to us right here. So 3.294 from Desmos here. 3.294. Just trying to be clear about what I did right here. Y equals 8x squared plus natural log of x, and y equals 88 is x star, what we called x star, equal to 3.294, right? Wasn't that the number we just got? 294, yes. Okay, so we've got our x location right here. I just want to point out real quickly, we're not quite done. We are interested in the XY location of the fly. So what we just found X star, right? We found the X location of the fly after that amount of time. I'm still interested in the fly's Y location, so I still just want to come back as my very last thing here, throw this into Y. Y equals x squared minus 1/8 natural log of x. And if we go ahead and throw this guy into our calculators here, I certainly pre-calculated this since I don't care about calculation that much. And we got a 10.701. Right, and I scratched out the word exactly right there just because that is Desmos rounding to 3 decimal places. We were unable to get a true exact answer for this one because not because of a calculus limitation, just because this equation right here, either you have an x trapped inside the natural log. The only way to get that x out of a natural log is with exponentiation, and then we would have an e to the x. So there's either going to be an x trapped in a log or an x trapped in an e to the power of, and we can never get them both out at the same time right there. So this was algebraically impossible right here, but still easy for us to go to Desmos and get a decimal approximation. Just got the decimal approximation for x in Desmos, plugged it back into our original position equation to get the y value, and now I can kind of conclude with the final answer right here. 10 meters is the distance traveled from 1-1 to this guy, not a straight line distance, but along the curve as described by the fly's position right here. So that's all I got for arc length. I'm very proud of myself for actually doing a short video here. I know that I've been having a couple long ones. Some are long, some are short. It's just the way that it goes. What I think you guys should be expecting for 8-2 is a very, very similar day tomorrow. I think that I think that this formula is easy. I think that coming back over to here, like I hope that on this page right here, you were like, well, that was about as simple as that could be right here. It's not the nicest looking formula directly, but when you realize that this is literally just the integral of the distance formula, I hope that that feels like really nice and easy for you right here. It's just one factoring happened associated with the distance formula, and that was it. which is really, really nice. It's easy to remember this one. If I ever forget this formula, I know I can come up with it on the fly in a heartbeat. This is not that bad right here. Our surface area one is going to be, I think, a smidge harder than this, but I think that this was like relatively easy. And again, I don't want to say this is easy. I don't want to be like rude and say that, but like this was relatively easy. Surface area will be a smidge harder, but it's not going to blow your minds too bad. The other thing that's going to be really nice is in 8.2 tomorrow, we're going to talk a little bit more. I want to talk a little bit more about this writing in green right here. How do you know that the circumference should be 2 pi r? That's my question for you tomorrow, and I would like to give you your hint. Your answer hint is we've already proven in this class, before we got this circumference statement right here, we proved a few weeks ago. We proved but when we did our first trig sub, in fact, our very first trig substitution problem was find the area of a circle. And we proved that the area of a circle was in fact pi r squared. So if you knew that the area of a circle is pi r squared, how do you know that the circumference of a circle, therefore, must be 2 pi r? And that's a question that we're also going to answer as part of our 8.2 video at the end of that one right there. So you should be thinking about that with some of our basic geometric relationships right here. How does knowing one of those pieces of information tell you what the other one's going to be? I'm going to kind of, since the next section, 8.2, is sort of like our very last geometry section of this class, I'm going to kind of state some like very generic geometric properties relating to calculus that you should be aware of that are kind of so big picture it's kind of easy to miss them. And then once you see them, you're going to say, "Oh my gosh, Tony, that was the coolest thing I saw all week." And that will be the case because it's pretty cool. So I'll show you guys that at the end of our 8.2 video once we get the last of our geometry ideas here in this course. So I'll see you guys for surface area in the next video here. Have a good one, everybody.